Okay, I did not tell you this before the test because I didn't really want to freak you out. But this traditionally goes down as the hardest test for the second semester, and for many students, the hardest test of the whole year. So this is not something new that I just dreamed up this year with this class. This is something I've done for the last few years because this tends to be a more challenging test that flubs some people up. My goal is for you to learn from the test and learn so you'll do better down the road. So that's the reason I don't mind giving a killer hard test and then letting you earn some points back on the back end. So here's what you're about to see on your piece of paper. You're going to see two numbers. The top number is what your grade's going to be if you don't do any of this stuff here. The grade below it has a P by it for possible. That's what your grade can become if you do all of the corrections as laid out here and get everything back right. I marked the correct answer on all of the multiple guess, so you should have something to work to there, at least in getting it there. So let's give those back. We'll talk a little bit about the explanation here of what you've got to do. There we go. Some of you have more than others to correct. No, these have not gone into RenWeb. No, notices have not gone home or anything like that. I'm going to send an email to you and your parents before I put it into RenWeb because sometimes parents freak out when they see grades. Okay? Wow. Laughter. Denial is what it, okay. Yeah, they're pretty closely related sometimes, okay? Okay. Yes, ma'am. You can think all the bad thoughts about me out there while you're there too. Okay. That's a good thing to do. Okay. Yes, this was very hard in a lot of places. On a few of these problems, when you go back and work through it, you're really going to be mad at me because you're just going to say, he shouldn't have done that. Okay? But then because you're going to look at it and say, I should have been able to see to get there, but he shouldn't have done that. Okay? But all of these problems came off of previous tests that were given in May for an AP exam. Okay? So none of this is just me trying to be mean to you. It's me trying to prep you for what you're going to see in May. Let's talk about test corrections. They're not due until March 10th. March 10th. Well, we can make it May, but then that's going to make the third quarter grade look really bad there for a long time. So let's March 10th. So after missions week, okay? So you've got plenty of time. I don't want you rushing through and just writing something down, okay? You can get half credit back on all on the multiple choice. They were 4 points each, so you can get back 2 points on each one of those. You can get full credit on the FRQ. Okay? Now, and you can ask for help from one another or from myself, and you can use, I didn't put it up here, but you can use your calculator. Yes, I did put it down here. You can use your calculator. Okay? When you turn it back in, don't give me just your corrections. Give me your test and your corrections. I've had students before that turn in, they made a 48 and they turn in a test corrections with 2 problems and think, well, why didn't I get all the credit back? Well, you only corrected 2 problems. I don't remember which ones you missed, so be sure you give them to me, okay? I had students that worked ones they got correct, thinking he won't know that, so he just gave me partial credit back. So I'm going to check to be sure that you get these correct all the way through. Don't try to fit it into this page here, okay? Some of you missed a minus sign. Still, don't fit it into this page. Go back. I want to see the problem and work. That's what I want to see. Put the problem number next to it. Don't make me guess, is this 5 or 7 or 9 or whatever. Work it completely, clearly. Try to stay in some orderly fashion, more orderly than I normally do my notes, where I kind of run around a little bit. Try to work down the page there. And give a brief explanation of what you did wrong the first time. I missed a minus sign. I didn't realize you could do this. I had no clue whatsoever, but now I understand. I'm not asking for paragraphs, just something. I didn't do this. I integrated when I should have taken a derivative. Something relatively simple there with each one of them, okay? So you've got that. You've got lots of time to work on that. You've got time to ask me or talk with your classmates on it. A lot of them you're going to see as you work through, oh, this is what I did there, okay? I don't mind you asking somebody else that got the problem right, how did you get there? My goal is for you to get there, okay? Remember, the top grade's what you get if you don't turn anything else in. The bottom grade with the P is where you can get to, okay? So all of you can wind up with very good grades in it here, okay? So, well, by my definition for this class, you can wind up with good grades for this, okay? Not by your definitions of what good grades are, but by my definition. Any questions about the test or the test corrections now? So you got some time to work on that. All right. Okay. Yes, sir.
Did you remember the website 20?
Would you send me an email so I can go back and get that corrected?
What do you mean?
You've gone back and done that, right?
Yeah.
Yeah, if you'll just send me an email to look at WebAssign 20, then I'll remember to go back in there and change it, okay? Yeah, I'll get it changed for you. I just haven't yet. All right, today we're going to finish kind of what we started yesterday. It's on a new lecture, 37, that says Applications of Differential Equations. Applications of diffeqs. So just to recap, differential equations have the variables and the derivative in it. Sometimes we draw slope fields to figure out what differential equations might be or solutions might be. The way that we learned yesterday to solve differential equations is by separating the variables and integrating both sides. So we try to separate the y's on one side and the y's on the left side and the x's on the right. Today we're going to talk just a little bit about some of the applications of differential equations. And probably the biggest application is something that you've already been using before calculus, and we alluded to it yesterday. Yesterday, if you look, or if you go back and look yesterday, we wound up with a differential equation like this to begin with, on the last problem yesterday. We had something that said the rate of change of volume is proportional to the volume. And that's a very common differential equation. The rate of change of volume is proportional to the volume. How much you've got of something makes a difference in how fast it's growing or shrinking. Does that make sense? I mean, think about people. You got two people, it's not going to grow very fast. But the more people you get, the faster it grows. So the rate of change depends on how many you've got there. So that's a very common differential equation. And we solved this differential equation yesterday and got down to something that looked like this. Y equals CE to the KT. Now, from now on, when you see something that says the rate of change of something is proportional to something, you can either write the differential equation and take about 6 steps to solve it, or you can just know the rate of change of something is proportional to something, Y equals CE to the KT. We're going to work through, you're going to find several examples that are like this. So this is the basic formula that we're going to be working with, and we got it from that differential equation. Okay? That's where we're at. So let's look at the next problem, or the first problem. The rate of change of Y is proportional to Y. If you write that down, that says dy over dt equals ky. Therefore, we know that we're going to wind up with Y equals CE to the KT. How do I know it's dy over dt and not dy over dx? Yes, if we read the rest of the problem, we say when t equals 0, when t equals 2, when t equals 3. Now, do you remember how we solved this type of problem yesterday? Right. We start plugging in to get good equations. Right. If we look at this, now we can plug this in and solve it, but again, hopefully you're getting to the point that you can realize this is called the initial condition. Initial condition when we started, because it says t equals 0. Anytime t equals 0, that's your initial condition. Whatever the y is for the initial condition, that's what our capital C is. Now you can solve that out if you want to. I can say y equals c e to the 0 power. It's not y equals, it's 2 equals c e to the 0 power, therefore c is 2. And that's what we expect, but that's going to be true every time that we start off with t equals 0. Now, if we start off with t equals 1 or something, if we wind up with something other than t equals 0 as a condition, we can't jump to that conclusion. But if you have t equals 0, c is going to be 2 if this was our diffeq to begin with. So we know now that c is that, so we can change our equation to y equals 2e to the kt. We go use the next set of data we got, 2 and 4. Y is 4 when t is 2. So now how do we solve an equation like that, 4 equals 2e to the 2k? We could take the ln, but we'd be better to do something else first. Divide by this 2 and then take the ln. It's easiest if we get e by itself to begin with. And then we take the ln of both sides, and we get k equals ln of 2 divided by 2. I'll be honest with you, when I'm working these problems, I know that's an ugly answer for k, but I'm going to strictly stick with that number. I'm not going to pick up my calculator until I get to the very end. I'm going to leave k as that ugly thing there. It'll just make it a little bit easier for me there. Well, now we know that our equation is y equals c, which was 2, e to this power, ln of 2 divided by 2. 2e to the ln of 2 divided by 2. Y'all comfortable? I'm sorry. All right. So now we haven't solved the problem yet. We're ready to solve it, though. What's the value of y when t equals 3? So now we just plug 3 in for t and we get our answer out. 2e to the ln of 2 divided by 2 times 3. And it looks like I get 5.65 out of that on my calculator. Do y'all remember doing this either last year or year before? Maybe. Okay. All right. Any questions about about that procedure? Pretty straightforward. This is something that you've seen before, I hope. Half-lives. Do y'all remember talking about half-lives? Probably what? Physical science, chemistry. Yeah. Chemistry. Okay. Half-lives. What is a half-life?
How long, like half of an atom, no. Yes, half of an element will decay.
Right. How long will it take for half of it to go away? When have you heard about this recently, or maybe in your lifetime? Half-lives. Why is that a concern with some certain things? Radiation. Big place where it's concerned at. Chernobyl happened before y'all's time, didn't it? But that half-life is concerned because all of that land is radioactive for 24,000 years or something or another before half of that stuff's going to go away. So it can be very, very damaging in that. So half-lives is a place that this is very important because half-lives or substances decay at a rate where the rate of change of that decay is proportional to how much of it is. So we have a basic formula for this, that is y equals C e to the kt. That's the common formula for radioactive decay. So when we're looking at this, suppose that there's 10 grams of plutonium-239 that was released in Chernobyl nuclear accident. How long will it take for the 10 grams to decay to 1 gram? Okay? How long will it take for the 10 grams to decay to 1 gram? There's our question. So we're looking for how long. We're looking to find a time out of this in the end. All right, so that's kind of where we got to go here. So how are we going to get from this to that with the information that's given? All right. What do we know? When t is 0, what do we know about y? How much did we start with? 10. Okay? Now, normally we have 2 points. Where's another point? Half. So when y is 5, what's t? The half-life, remember? This is the half-life, 24,100 years. Okay, so we can use that information, and that's something that you would not be expected to memorize, okay? This would be given to you. The half-life is 24,100. So now we've got 2 points. When t is 0, y is 10. When t is 24,100, y is 5. Now we should be able to figure out what our c and our k are from that. So let's do that. Are y'all comfortable with using this first constraint and saying that c equals 10? Because when t is 0, y is 10. If I put 0 in place of t right here, I'm going to get c equals 10 out of it. So I get, actually to do the next part, I can say 5 equals 10 e to the 24,100 k. And now, what's the next step? Divide by 10. So we get 1/2 equals e 24,100 k. Introduce LNs. Wow. So k is the ln of 1/2 divided by 24,100. Now again, I'm just going to plug that in like it is because k is so small here. If you just try to use whatever your calculator gives you, you could get off by a huge amount there. So we know that our equation is y equals 10 e to that power, ln of 1/2 divided by 24,100 t. And that e to the ln of 1/2 divided by 24,100 could be simplified if you wanted to. I'm not going to because I don't think, since we've got a calculator, I don't think it makes it a lot simpler. So now we've got our equation. What do we do from here? The question was, how long will it take for it to be 1? Where do we plug 1 in for? 1 is y this time, okay? Because 1 gram, so 1 equals 10 e to this power, 24,100 t. 1/10 equals e to this power. All right, then we're going to introduce LNs again. Why do we need to introduce LNs? To get rid of our e, to get this t is in the exponent, so we've got to get rid of that. So we get the ln of 1/10 equals the ln of 1/2 divided by 24,100 times t. And if we finish off with that, we get 24,100 times the ln of 1/10 divided by the ln of 1/2. That's what our t is. And if you punch all that on your calculator, you get 80,000 years. So it'll be 80,000 years before that 10 grams that was let loose goes down to 1 gram. Pretty long time. Can y'all think of another place that science uses something like this? Fossil dating, yes. It's used quite often to say that the Bible's wrong because the fossil dating says that says it's this old when the Bible says it's not that old. But science does use this for dating things with carbon-14. How can it be that the science says one thing and the Bible says a different thing? There could be an argument for that. I think you could also make the argument if God can make it all, couldn't He make it look like it was older than it is? Okay, we'll leave that for your thoughts right now. Okay.
Although, I mean, I'm just saying, when Adam came into the world, what age was he? Well, you know, he obviously came into the world without an age,
but he had to have an age.
Yeah.
Because he was just poof here, but yeah, he didn't have an age, but he had an age. So I think I could easily argue, I think, the fact that if God made it anyway, He could make it look however old He wanted it to make. Okay, supposing this population of fruit flies. Does anybody work with fruit flies? Are y'all doing that in AP Bio or Anatomy? Yeah. In AP Bio, okay. Fruit flies, yes. There's usually a lot of moans that go through when we mention fruit flies, okay? An experimental population of fruit flies increases according to the law of exponential growth. There were 100 flies after the second day of the experiment and 300 flies after the fourth day. Approximate how many flies were in the original population. Can we jump to the conclusion that this is our equation? Why? Exponential growth, yes. Exponential growth is the same thing as the rate of change of y is proportional to y. Exponential growth, this is what that is. Exponential growth because you've got an E in it. Now, what's different about this problem? Who can tell me? Yeah. That's right. We want to know what y equals when t equals 0. So we're kind of working backwards. We know when t is 2, y is 100, and when t is 4, y is 300. But we're trying to work backwards on it there. Can you handle that? All right, I'll give you a couple of minutes to go with that, see how far you can go, and then we can pick up and help you if needed there, all right? Yes. For some reason, why do y'all use them in biology? Why are they important to study in biology? Do y'all know?
Question. Yeah. I did not like that experiment every day because it was gross, but
okay. Okay, because they reproduce so quickly, it's easy to see the change. Okay, that makes sense. That makes sense. Oh, yeah. Because they,
Be online one, but like probably the real one.
all right, so what's different on that first plug-in? We still have two variables there. We can't figure out what C or K is. Well, does the other one do us any better? Oh, it doesn't. So now that causes a conundrum maybe algebraically. However, we've got two equations with two variables in them. So algebraically, we should be able to solve this. Anybody got some ideas?
Well, I don't know if this is right, I'm just thinking, but what if you like plugged in both and you get like y equals 100 and, oh yeah, you have it right there.
Okay.
What if you multiplied the hundreds on both sides by 3?
Okay.
And
So if we did, so she's saying make this, we're going to multiply that one by 3 and make it 300 equals 3c e to the 2k. And now since these two are equal, we get c e to the 4k equals 3c e to the 2k. Right? There's nothing wrong with that algebraically, but we've still got one equation with two variables in it. Yes, that would be the thing to do. And nothing's wrong with this, but it'll actually be easier if we go back and solve one of these two equations up here. If we solve one of the original ones for C or K1, I think C will actually be easier, and then plug it into the other one. So let's take this top one, and we'll say 100 over e to the 2k equals C. That's just dividing by e to the 2k. Well, that's C's in both of them, so now I'm going to take that and substitute it back into this bottom equation in place of C. So I'll get 300 equals 100 over e to the 2k times e to the 4k. Now that looks confusing. Is there any cleaning up we can do there? Right. We've got the same base with these here, one in the numerator, one in the denominator. So we can just subtract 4k minus 2k, and we can just get e to the 2k. So we get 300 equals 100 e to the 2k, and that looks very similar to what we started with. Agreed? And it looks very similar to what we had earlier in problems. Now that's a solvable problem. If we divide, we get 3 e to the 2k. So ln of 3 equals 2k. So k equals the ln of 3 divided by 2. Actually, let's show you this in case you don't know it. Good time to show you something calculator-wise here. Are y'all familiar at all with storing variables in your calculator? Okay, this is something that would be beneficial for you then, okay? Let's go ahead. Did that go off? Let's go ahead and calculate what K is. All right, so I'm going to, on my calculator, ln 3 divided by 2. Whoops. Make sure you close that parentheses there. That's what I want to do, ln of 3 divided by 2. Press enter, and it's going to give me this ugly decimal. Well, now I could write it down on my paper and have to type it back in every time, but you can also find the STO button on your calculator right above on, and press STO, and it gives you answer and an arrow, and then any of the letters that you see here in green, I'm going to use A, so I'm going to press alpha math, it says answer A. That's going to store that answer in the A memory slot, okay? So now if I say 2 times alpha A, it multiplied that number by 2. Big deal there, okay? So now we've got this stored into our calculator memory. That's going to be beneficial to us. So we know what K is. Do we know what C is? No. We had C was this figure right here, right? Remember, we had solved and said C is 100 over e to the 2k. It looks like C should be 100, doesn't it? Based on this here. But remember, we got to this a different way, and we could call it 100, but we're not going to. We could call C 100, but we're not going to do that. So,
it's because it's only 100 at that point.
Right. So let's figure out what C is then, and now we should be able to use our calculator for that, shouldn't we? We can say 100 divided by e to the 2k. I'm going to say 2a, and notice it's just going to put a on my screen, but now it tells me that C is 33 1/3. Okay, if I wanted to store that, I could store that in B and have both numbers stored in there. The question was, how many did we start with? Can we answer that now? We just found C. How does C relate to how many we started with? Anybody remember? Yeah. Remember that C should be the initial number. So there's no reason to do any more. We can say that there's about 33 or 34 fruit flies to begin with. Probably was 30. I mean, who knows? 33 or 34. But that's a common way you may have to solve problems as well. That's the only reason we worked through these 3 problems today, was because all of those are just different ways to solve problems that you may run into. Do we feel comfortable enough working these? Okay, I see one yes. Do we feel comfortable working these? All right. I don't mind working through more, but I don't want to belabor our time here. You have other pressing things you could be working on. So you have obviously things you can be playing with and working on. So I will give the floor to you.